Hi guys, so today we're going to look at inverse variation. So inverse variation is going to be very similar to something you did in Algebra 1 that was called direct variation. In fact, we're going to do a very similar process, but our operations are actually going to be flipped. Now, direct variation was what we talked about back in Algebra 1. So what you learned is that if something varied directly, if there was a constant that tied those variables together. To find that constant, we did y divided by x, which was very similar to the concept of slope. So once we knew what k was, we could write an equation that related y to x, which looked like it was this form where k was that constant. Again, it looks like a linear function where k is your slope. But what's specific about this line, it can't just be any line for it to vary directly. It has to be a line that passes through the origin, because if you notice, there is no y-intercept to that line. It is just a slope times x. And then the last thing about direct variation, if you had a table of values, if you want to see if it varied directly, what would be true there is that the quotients in that table, so if I did y divided by x, again, very similar to slope, that value would be constant throughout the table, and that's a way we could tell if those points were varying directly. Inverse variation, very similar, except our constant, instead of doing y divided by x, our constant is found by doing x times y, which means my equation then is going to be k divided by x. And now what this would look like then as a graph, this is actually going to be a pretty good introduction to rational functions, because that's similar to what our shape's going to look like. And then just notice your end behavior there. As x approaches infinity, y is approaching 0. And as x approaches 0 from the right side, y is approaching infinity. And these are just talking about if we're looking at positive values like real-world situations. Then if we're looking at a table of values, the products in that table would be constant. Again, that's because the constant's found by multiplication. So let's look at an example here. We're going to figure out if these relationships are a direct or inverse variation. So I think the easiest way to do this is to solve for y. And then from there, we can look and see what our equation looks like and which equation it matches up to. So on this first one, I'm going to divide both sides by x. And if you look, this looks exactly like our inverse variation. Okay, where k would be 5, and this would be an inverse variation. All right, look at b. Now this looks similar to our direct variation except for this -4. But think about what you guys know from Algebra 1. -4 would be the y-intercept, which means it does not pass through the origin. And direct variation has to pass through the origin. So this one is actually going to be neither. Then my last one, to get y by itself, I'm going to multiply both sides by 2. So I get y equals 2x, which is direct variation. The constant there would be 2. Again, table of values, what we're going to do is we're going to look at the quotient of x times y. If that's constant, it would be an inverse variation. Direct variation, we would look at y over x. Again, think about lines, think about slope. It's y over x. So if I were to multiply these values together, I do not get the same thing. So this is not an inverse variation. If I do y divided by x, though, every time I get the same value. So this table does represent a direct variation with x and y. Again, if you were to plot those points in a graph as well, that could help you. You could see that it is just a straight line that does go through the origin. All right, then let's look at this next one. If I start by doing x times y, every single time I get 60. So I don't even need to check the other option. This is an inverse variation. And again, look at your graph here. So 160, 230, 320, 415. It's going to follow that same pattern as well. All right, so now let's look at some algebra examples. So what we're going to do is we're going to find these values given some information. Now what's important here to pay attention is it tells us if it varies directly or inversely. So if it varies directly, remember that's like slope, that's like a straight line. So my constant, again, which is like slope, is y divided by x. Okay, so if y is 3, x is 6. So that's 3 over 6, which I can reduce to 1/2 if I want to. That is my constant of variation. So now if I want to solve for that, I can set up an equation if I want. My equation would be y equals 1/2 x. And then I can use that equation to find anything. Specifically, this wants me to find what is y when x equals 8. So all I would do is plug in 8 for x, and I get that y is equal to 4. All right, and then if y varies inversely, okay, again, let's find our constant first. Okay, so these are the same x and y values, but my constant this time is x times y. That means my constant here would be 6 times 3, which is 18. All right, my equation also looks different. It would be y equals 18 divided by x. All right, so I want to know what is y when x is equal to 9. So again, just plug in 9 for x. And I get that y is equal to 2. All right. So now last thing we're going to look at is just a couple of word problems. Very similar process to what we just did, but we need to find what our variables are by reading the problem. So example 4 tells us, Kim lives in a suburb and drives to work in a city. The time in hours it takes her to get to work varies inversely with her average driving speed. Okay, so what I'm going to do is inversely, which means my constant is going to be x times y, or in this case, t times s. Okay, so her speed varies inversely with her time to get there. So it tells us she averages 20 miles per hour in heavy traffic. If that happens, it takes her 1.5 hours to get to work. So let's find our constant of variation then. So then it's going to take her 1.5 hours to get to work if her speed is 20 miles per hour. So that gives us a constant of 30. Then we can use that constant to find my answer here. Now, to make this a little bit easier, I'm just going to use the same equation that I had before. So k is equal to t times s. Well, now I know k is 30. And let's look at the information it gives us. It says, how long would the trip take if her average driving speed is 50 miles per hour? So we're trying to find the time if her speed is 50. So then all I would need to do, solve for t, is divide both sides by 50. So t is equal to 3 over 5. So that's 3/5 of an hour. So if we want to convert that, we can. 3/5 of an hour, we would do 3/5 of 60, which would be 36 minutes. All right, again, with inverse variation, just remember, what's nice about these, if you think about these, again, as a graph, inverse variation, the graph looks something like this. So as one variable, as my x is getting bigger, my y is getting smaller. So look at this case. It took her, if her speed was 20 miles per hour, it would take her 1.5 hours to get to work. Whoops, put my dot in not a very good spot. 20 miles per hour, here's, let's say 1.5 hours is up there. If her speed is 50, okay, it's taking her less time, which also just makes more sense as an actual real-world problem. If you're driving faster, it should take you less time to get to work. So again, 20 miles per hour, an hour and a half, which is 90 minutes. Okay, 36 minutes when we're going faster. All right, last example. The time and hours it takes a group of volunteers to build a playground varies inversely with the number of volunteers. So K is equal to T times N. It takes a group of 10 volunteers 8 hours to build a playground. So my constant then is going to be 8 hours times 10 volunteers, which is 80. So 80 is going to equal t times n. And then we can use this to find any information we want. It wants to know how long it would take 12 volunteers to build a playground. Okay, so we know my constant is 80. I don't know the time. I do know that the number of volunteers here is going to be 12. So divide both sides by 12. And then I'm going to get 6 hours, and then I'm going to have some minutes left over. So 12 times 6 is 72. So I'd have 8 over 12 as a remainder. So I need to turn that then into minutes. Okay, so 8 over 12 times 60, and I can just, let me go ahead and reduce that to make it a little easier. So this is 2 over 3, so 2/3 of an hour. So 2/3 of an hour times 60 gives us 40 minutes. So this is going to be 6 hours and 40 minutes. And again, it would make sense here. Okay, more people, it's going to take less time. Okay, 10 volunteers, 8 hours. 12 volunteers. Okay, again, more volunteers you have, the less and less time it's going to take. And again, if you think about it, it's never going to take a 0 on that time. So even though this is going to get closer and closer and closer, it still has to take some time to make that playground. Even if it's 100 volunteers, it's still going to take something. It can't just magically appear on us. But that concept is something we're actually going to look at when we look at rational graphs, which is going to be the next thing we do tomorrow.